afternoon, everybody. So I'm Jean-Sébastien, and I had the pleasure to manage a project for the past few years, and also to lead the work that we carried on the demonstrator. So the demonstrator is named Mona Biop because it's financed both by the Monamo project, but also by Abiop Plus project. This work consisted mainly of the design, the procurement, assembly, installation, and operation of the demonstrator. Itself, as I will detail it in the next few minutes, consists of the buoy, the mooring system, and the instrumentation, so the monitoring subsea, but also the onboard instrumentations. And this demonstrator, the main purpose was really to measure the tension and the elongation on the nylon ropes in real conditions. So thanks to the sensors that Peter presented to you a few minutes ago, and also validates these sensors, so the elongation sensors, but also some other innovative sensors like the one from NCD that was included in the ropes, and in general to gain experience in the operations and the design of PA mooring ropes, mooring system with PA ropes. For this demonstrator, we had, together with a consortium, we had some design basis, and the main, which was quite simple in the end, but the main criteria was to have a quite significant pretension, which corresponded to 15% of the braking load, and of course to satisfy some safety factors criteria. So in this case, we looked in 10 years return period conditions, knowing that it will be deployed only for a few years. In general, it was a bit challenging in the design sense, as this is a small buoy. For this kind of floaters, usually it's empirical design. In this case, we went really analytical and had a quite advanced modeling, including both the potential and the Morrison model. To go quickly, so we of course work with suppliers for the buoy, but also for the PA rope, and Karel that will say a few words later from Bexco was a key partner, of course, in the Monamo project, and supplied the ropes that went offshore. And we also had other partners suppliers for the mooring system, mostly FMGC for the anchors, and Carlier for the chains. Oh, sorry, I'm trying to go to the next slide. Yeah, so we decided to deploy this demonstrator at the Mistral test site, which you can see on the bottom at 3 different levels of zooms. So this test site is, the lease of the site is owned by Valeco and BW, and it's operated by OpenSea. So that is the Mistral test site. As you can see, it is located on the eastern part of the Gulf of Lion, between Spain and Marseille. And of course, you may be familiar with the area since the first prototype farm was deployed nearby a few months ago, PGL, Provence Grand Large. In this case, for our demonstrator at the Mistral test site, it's only 3 nautical miles from the coast. So it's a very short fetch for the north wind. The water depth is 57 meters. And of course, I didn't include it in writing, but we decided to go for a 3 lines mooring system. So we have 1 line going north, another southeast, and another southwest. And as you can see, the the southeast line, so the line number 2, is a bit longer, and that's also because that's the direction where we have the highest wind and the highest wave. From the north, it's the fetch is very small, so the waves are not so strong. Still, there are quite often some wind and short waves from the north. So these 2 lines, number 1 and number 2, to the north and to the southeast, they are quite solicited, and that's where we had nylon ropes, as I will detail in the next slide. Yeah, and we also implemented together with the authorities an exclusion zone, so there is no navigation allowed around the buoy. So this, I present here the final design of the full system, excluding the monitoring, which was already presented. Also, on the left, you can see the buoy, which is all in all, sorry, looks pretty standard, but is a custom design. So that was also some work together with Gismart to customize it and make it fit for purpose. It contains an energy production and storage system with solar panels and batteries and so on. You can see also the mooring system itself is made of, well, the anchors from where we use, so it's cast iron blocks from FMGC, which we assembled together with a chain. And then we had some chain segments, but also nylon segments, of course, on 2 nylon segments close to the buoy, on which we placed the tension or the elongation sensors, and where we measure the tension. But we also have some segments on the seabed to evaluate the abrasion and the long-term reliability of the pier ropes on the seabed. Here a few slides showing the configuration of the ropes or of the full line. So in white you can see the pier ropes in a static condition on the left and in extreme condition 10-year return period on the right. Well, you can see the lower segments on the seabed, and so the first two are line number 1 and 2. The third one is it does not include the line number 3, does not include nylon ropes, and you can see that the bottom segments are totally lifted, of course, in extreme condition. What you can also see, although it's not zoomed up so clearly, but the waves may come above the buoy or close to the top of the floater. So that was also why its design was not was a bit tricky, because we have quite a large vertical load from the mooring lines imposed by this criteria of 15% pretension. I will show it afterwards also. Here are a few pictures of the assembly. I skipped the procurement part. It's not so much to talk about. It went pretty straightforward. So the assembly was done at the quayside of the installation contractor, Foselev. So here you can see the buoy assembly. Well, that was on the anchors. While we tested the assembly also with how to say using chain to connect the two anchor blocks together, which was worked quite well. We also assembled all the instrumentation. So on the left here, I'm not sure if you see my pointer. On the left there is energy cabinet with the so is the charge controllers, and in the middle there is all the instrumentation, so onboard PC and so on. And you can see also on the buoy, besides all the line sensors, we also had motion monitoring, quite advanced motion monitoring with 2 GPS antenna. And of course also we had some communication antenna, one Wi-Fi and one 4G antenna, in addition to a backup satellite positioning system, which we have on all our buoys. And we also tested spread out the PA ropes and check the length. And one part that took quite some time was also the connection of the upper piece of chain between the buoy on the upper PA segments, and that included all the instrumentation cables, which on purpose we added some overlengths such that they are not tensioned underwater, as we can see later. So the installation, well, we had some preparation activities, obviously. The vessel used was a Castor 02 from Foselev Marine. There's a very convenient gantry crane with 3 hooks on the stern, allowing to overboard the buoy and upend it. So that was tested at quayside. After that, we immobilized it, and it's all in all, it's more than 80 tons on the deck. So when you have it on the stern of the vessel, Of course, the vessel is the freeboard is not so high. During the installation, so we deploy the anchors using the country crane again, and deploy the chain and the PA ropes. So the two first line, we deployed them mostly slack with a little tension. After that, we overboarded the buoy with, you can see the third line, where you can guess the third line is already connected to it, the one made only of chain. And you see also all the sensors pre-mounted with the instrumentation cables. So these are for the line number 1 and 2, the one with the nylon segments. Once the buoy was in the water, we had divers to connect this the nylon segment, so pre-led to the buoy. And as you can see, the buoy is floating quite high at this time. After that, we installed the last line, and we one specificity for this installation, and that was how to say, helped or allowed by the monitoring system, which we had running during the installation, was that we deployed the we deployed the third anchor under tension, such that we had the target pretension on the mooring lines. So to do that, we monitored the tension on the lines during the lay of the third line on the laying of the anchor. In the end, you can see that the buoy is floating much lower with the design condition, of course, than before, because we had 9 tons of vertical loads from the mooring lines, 4 tons in each line. Following the installation that took place in February, we carried, of course, well, the first thing we do is that we monitor the data that comes out of the buoy, and we verify that everything works fine. So that is an ongoing activities, and we also had regular subsea inspections. You can see a few pictures of it by divers, and also some instrumentation maintenance. And you can see here also the cabling, so obviously the chain and the keel of the buoy, and also the cabling for the sensors that are looking quite well. That's all from my part. Thank you for your attention.
Yes, thank you, Jean-Sébastien. Romain, if you want to continue the presentation.
Yes, thank you. I guess you can see my screen.
Yes.
Okay. So this slide is just a reminder of the sensors we deployed SMC, and I will present you the results of a comparison between sensors data and behavioral law model, so polyamour law model. And to do this comparison, we used the load cell data and wire transducer data. And we used also the positioning system with INS that Jean-Sébastien presented you before. We automated, in fact, the post-treatment of the raw data of the INS system with a base station onshore, which is close by the Mont Nambiop buoy. So we get a centimetric accuracy on the position. Yeah, the first graph I show you here on the left of the screen is the tension graph, long-term tension. You have 6 months of measurements here of the 2 load cells for each line. First, what we can see that the pretension is and the mean tension is pretty stable, near 40 kilonewtons. And we can observe as well that both lines went through high loads events around 28% of the MBL. Okay, and we will have a close look at 1 hour during a storm on this on this load event, where the load went up to 92 kilonewtons, which is 32% of the MBL. So we have tension recording, elongation, positioning of the buoy. All the data is sampled at 10 Hertz, and everything is synchronized. Okay. So to cross-validate the polyamour model, the behavior law of the nylon and elongation sensor measurements, we did set up a deep lines model. The first one is a pure traction test setup. We used the low coefficients, the coefficients of the low identified in a laboratory. And so the model itself is a 1.33 meter long rope. On one side it is clamped, and on the other side we impose the tension sensor recording for 1 hour. So one run is computed in 15 seconds using the behavior law. And we did 2 runs. The first run we did was with the full behavior law of the polyamour project with the viscous part. And we tried also another run with the elastoplastic law, which is the law simplified without the viscous term. So you can have a first overview of the results here with the sensor in orange, and in blue you have the simulation results for the 2 runs. Okay, so I zoom here on the maximum amplitude event. In orange the sensor, in dark blue the law with the viscous behavior, and in light blue the elastoplastic law. So you can see that in low tension range we are not perfectly accurate, but for the rest of the curve it's pretty satisfying. And on the right here you can see the ellipse showing the viscous behavior of the nylon material. Dark blue, the ellipse as well with the viscous part of the model, and in light blue the elastoplastic law. So to get a bit more of understanding of the model error, I did define a metric to monitor the error, which is the difference in elongation between the sensor and the law divided by the initial length of the rope. And this is what we get. We can see that with the elastoplastic law, the error is really increasing when we are in a low tension. And when we add the viscous part, the error is much lower. But still, on the low end of the data set, we can see that the error is rising. Probably we can improve some part of the behavior law, as Laure mentioned previously. Okay. So now we'll go to next second phase of the study, which is a validation of virtual sensor methodology. So let me give you 2 words on this methodology. We use outputs from real sensors, and those outputs we use them as input of virtual sensor processing. A virtual sensor processing can be both either data-driven or simulation model-based. Both techniques allow to either replace an out of order sensor or detect anomalies from the data. But if you use simulation model-based, you have additional advantages. With the simulation model, you can access to any variables from the simulator. So in our case, on the 3 mooring lines, you can access to the mechanical state of any point of the model. So in our case, we use the INS positioning, centimetric accuracy, and we force in the global model with the 3 mooring lines modeled, we force the movements. And so to do so, we needed first to calibrate the model. So it is a process which started, in fact, during the design of the buoy itself. We needed to first identify variables that we are able to measure, then perform measurements on field, for example, the mooring line lengths, etc. And then, based on as-built data, we calibrated the model with very simple routing here, which can be much more complex if we want to have a better accuracy. So we set up this deployment model used for the design of the buoy. We impose the 1 hour of buoy movements at 10 Hertz. For this time, we only use the viscoelastoplastic nylon behavior law. And this is what we get. We can observe on the top left graph that actually the tension calculated by the model is pretty close from the tension sensor itself. This is on the maximum amplitude event. And if we have a look at the error on the full dataset for 1 hour, we can see that we have about the same behavior that we have on the previous traction test, meaning the error is raising for low tension and is below 1% of the MBL for the mean tension, and go a bit above at the top tension event. On the bottom here, I did plot the elongation predicted by the model, the global model in dash blue. We have the measurements from the elongation clamp in orange, and I also plotted the calculated elongation from the pure traction model I presented before. So the viscous law on the pure traction model. What is interesting here is that in fact both models have the same order of magnitude of errors. Of course, because there are much more uncertainties on the global model, we have bigger error, but we can see that for this event, for example, we are in the same order of magnitude. So I understand that if we keep improving the behavior law modeling, we will gain also on more complex global model, that the kind of model we use for floating wind design. Okay. So what we learned from these comparisons? Well, first, elongation sensors gave quite reliable results even if they have room from improvement, in particular for long-term measurements. The mean tension is quite stable at about 15% of the MBL, and we have even after 4 months of immersion and in real life environment, we have a good fit between the nylon model and the mooring lines. Okay, and for the validation of the virtual sensor methodology, in fact, we were pretty satisfied by the absolute error we have on the sensors. I mean, on the tension, especially because we used a very minimal mooring model calibration process. We had higher errors for low tension values, with significant contribution of the behavior law model error. And yeah, I wanted also to mention that for this kind of methodology, the uncertainty management of the position data was an important part of the work, even if I did not really go into detail about that. Yeah, that's all for me.